Hello, everybody. Welcome back to another video. I hope you're all doing well. In this video, we're going to be taking a look at a question from the IB Chemistry Paper 2HL from May 2017, and this is from Time Zone 2. Now, I mentioned in my previous video where I will be moving on from topic 8 questions after a video or two, and I think this is going to be the last video I will be making on topic 8 because I believe I have covered about 95% of the type of topic 8 and 18 questions they can ask in the exam. So if you go and watch my other 2 or 3 previous videos and this one as well, I think you are set for topic 8 and 18 for the exam. In addition to, of course, some more revision and practice questions and some other topics that you need to cover. But other than that, I think you will be set mostly. Now, this kind of question is very common. I'm sure to those who are in IB year 1 or even 2, you know these kind of questions come up a lot with this graph and this pH curve. And, you know, they will ask you small 1-mark questions like this about deduce the pKa or give a strength or reduce the strength of the acid, giving a reason. And I'm going to tackle this question over here. Now, the first thing I need you to understand is what exactly is going on here. For a very long time, I didn't understand what was going on. I didn't know how they're getting this graph. I had no idea what they're doing to get this graph, because my teacher never gave me a diagram, right? So I'm going to give you a diagram. I'm going to exactly explain what is happening or what experiment is going on in order for us to get this graph. Now, this is a titration reaction. A titration reaction is when you, in very simple terms, when you very slowly add something to another liquid and you observe the changes that happen using a pH probe or a thermometer or with your eyes if you are monitoring color change, for example. Now, this is kind of how the setup looks like, you know, with relevance to the question. Over here, we have NaOH, which is sodium hydroxide, being added to an acid. We don't know what kind of acid it is, but we know it's an acid. So we have a beaker of acid. This is the acid inside it. Now, remember, inside the acid, you not only have the acid, but you also have water. You have some H2O as well, right? It's very rare that you get pure solution of acid. Usually it has water inside it. So you have this acid and you have this little tube-like thing over here. It's called a titer, I believe. I'm sure you must have seen it when doing experiments in school, something like this. And usually it has liquid inside it and it has a knob over here, and you kind of turn the knob and drops of this is let into this solution. So inside the beaker, as I said, we have acid and water. And inside this tube, we have NaOH. And we have this funky looking device over here. This device over here is a pH probe. So it basically monitors the pH of the solution. I don't know if this looks like a pH probe, but I'm just making a random drawing. This monitors the pH of the solution, and it records all the changes that happen in the pH of this acid over here as you continue to add the NaOH. And usually this it's connected by using a wire to like an iPad or something like that, and that iPad is constantly graphing the change. So this is how we get the graph. So as we continue to add NaOH, changes occur in the solution, in terms of pH, and these changes are then monitored by the pH probe. And the pH probe then sends this information to the iPad, and the system in the iPad designs a graph which looks something like this. Now that we have got how we've got to, now we've understood how we've got this graph and what exactly is happening, let's dissect it. Let's take a look at it and let's see what we can understand from this graph. In the first question, they've asked a state giving a reason the strength of the acid. Now, how do you tell this? How do you tell this what the strength of the acid is? Because they've not told us what the strength of the acid is. They've told us that they're adding the base NaOH, and we know that NaOH is a strong base, but they've told us nothing about the acid. Maybe the first clue that you can get about the strength of the acid is from the starting point of the pH. So this starting point over here, this starting point is the initial pH of the acid. It's the initial, please, I'm so sorry for my handwriting. It's the initial pH of the acid. This is when no sodium hydroxide has been added. So the initial pH is about 3. And usually for strong acids, the pH is much lower than this. It is around 1 or maybe a little more than 1. But having an initial pH of 3 is a sign that this is actually a weak acid. But this is not enough. This is not enough evidence for us to make this deduction. Let's move on to the next part. We have some vague idea about what it could be, but we're not 100% sure yet. We need more evidence. So let's move in the graph, and we see that, okay, the graph moves like this, and then, oh, it suddenly shoots up. At 25, when we've added 25 centimeters cube of NaOH, the pH has this dramatic increase. What happens over here? What is this vertical region? Well, this vertical region is the point at which the number of moles of NaOH added and the number of moles of acid is the same. That is represented by this vertical region. So really what is happening is that as we continue to add NaOH, as you know, is a base. So NaOH, when we add it, it reacts with whatever acid is inside over here. I'm just going to call it HA as acid. And then it produces water and a salt. I don't know what the salt is because I don't know what the weak or strong acid is, but I know that it produces H2O and salt as a result of the reaction. So as we continue to add NaOH, we can see that the acid is slowly beginning to deplete, right? We have less and less acid and more Na or more and more NaOH in the solution. And that causes the pH to rise because the solution is becoming more basic. So at the equivalence point, we have an equal number of moles. We have equal number of moles of NaOH and equal number of moles of acid added. So that would mean that the equivalence point, the pH at the equivalence point should be 7, correct? Because if you have the same number of moles of NaOH and you have the same number of moles of the acid, then the pH or the pH at the equivalence point should be 7. It should be neutral. It should be neither acidic nor basic because both of them are in equal amounts. But over here, we can see that the equivalence point, and how do you determine the equivalence point in this long, because this whole thing is not the equivalence point. This whole thing, this whole thing is not the equivalence point. The equivalence point is actually the mid part, the mid section, the midpoint of this vertical region. And the midpoint of this vertical region is approximately here, right? And you can see that this is not 7, this is around 9. So the equivalence point is around 9. That is odd, isn't it? Because by logic, at the equivalence point, we should have a pH of 7, but we don't. We have a pH of 9. And that is actually because the acid is a weak acid. And why does a weak acid have a higher equivalence point? Let me show you why. Let's assume that this weak acid is ethanoic acid. Okay, I'm just going to take some random weak acid. Let me just erase this diagram. So let's imagine that this weak acid, there's some weak acid. I'm going to consider it as ethanoic acid. It is reacting with NaOH. We are slowly adding NaOH to it. So it produces a salt, which is CH3COONA plus H2O, water. We established that below. Now this salt over here, it actually reacts with water. It reacts with water and it breaks apart. It breaks apart into two different elements, I guess you could say. So it breaks down into Na plus and CH3COO minus. Now you know that the conjugate base of a weak acid, this is the conjugate base of this weak acid, is a very strong base. So the conjugate base of a weak acid is a strong base. And this CH3COO minus, the ethanoate ion, you could also call it, then goes and reacts with water again, because remember, there's lots of water present in the acidic solution. So it reacts with water, and this base, it acts as a base, of course, and it steals one hydrogen from water. So it becomes CH3COOH again. It returns back to its original state, and water becomes OH minus, hydroxide. And you know that hydroxide has basic properties, right? It increases the pH. It has basic properties. So that's why for weak acids, only for weak acids, the equivalence point on a pH graph is above 7, because the conjugate base of a weak acid is a very strong base. This does not happen for strong acids. Remember, strong acids do not do this. If you add the same number of moles of strong acid and the same number of moles of a weak or of a strong base, like sodium hydroxide, your equivalence point will be at 7. However, this is not the case over here. So the reason that this graph, or the reason that the acid is a weak acid, now we've reduced the fact that it is a weak acid, is because the equivalence point sorry, give me a second. The equivalence point is greater than 7. I'm very sorry for my handwriting. Hopefully you understood that. So it is a weak acid, and it's a weak acid because the equivalence point is greater than 7. And hopefully you have also understood why the equivalence point is greater than 7. Hopefully you've understood that as well. Now, let's move on to the next part of the question. Now, and this part, I've seen it come up in, oh my God, so many papers, and it's actually very, very easy. Deduce the pKa of this acid. You only need to know one fact in order to tackle this question. The pKa is equal to the pH. In such graphs, the pKa is equal to the pH at half the equivalence point. Now, what does that mean? You may be a bit confused. What do you mean the pKa is equal to pH at half of the equivalence point? Well, how much volume of NaOH should we need to reach the equivalence point? We needed 25 centimeters cubed of NaOH. So what would half of this be? If we add half of this, that would mean that we have reached half the equivalence point, correct? If you need 25 centimeters cubed of NaOH to reach the full equivalence point, you would need half of that to reach the half equivalence point, correct? That makes sense, right? So that would mean that we need, what is 25 divided by 2? 25 divided by 2 is 12.5. So we would need to add 12.5 centimeters cubed of NaOH to reach the half equivalence point. And we know from our information over here, this little information that I've given you, that pKa is equal to the pH at half the equivalence point. So what is the pH at half the equivalence point? Well, we know that we need 12.5 centimeters cubed of NaOH to reach half equivalence point. So let's see, where would 12.5 be? Well, it would be about approximately between here. And if we just kind of extrapolate over here, we can see that at half the equivalence point, the pH is approximately 5, around 5. So we can deduce, sorry, I've drawn this a bit badly. So it's about here, right? So if the pH at half the equivalence point is 5, and we know that the pKa is equal to the pH at half the equivalence point, we know our answer. The pKa for this acid is 5. That's it. That's how simple the question is. Hopefully you have understood that. That's it for this video. Thank you so much for watching. I know the first part is a tricky concept to understand. Even I did not understand for a very long time. So if you still don't understand it, that's completely fine. Or even if you don't understand the second part, please feel free to reach out to me on my social media or my email, or send me your questions via my DMs, and I'll be more than happy to help you out. Thank you for watching. I'll see you in another video with another question, and take care of yourselves. Goodbye.